was the idea behind input preprocessing. So you have your data matrix X, whose rows are X1 transpose, X2 transpose, and up to Xn transpose. Okay, so, and what is an input preprocessing? Basically what we do is we take each data point, X1, X2 up to Xn, and transform it into Z1, Z2 up to Zn. Okay, so we've seen transforms before. We've seen the nonlinear transform before. No different here, except that the goal is different. Okay, here we're not doing any fitting, we're not looking at any y values, nothing. Okay, there the goal was to address E in. Here we're just trying to put the data into some normal format. Okay, and this transform from Xn to Zn is going to be implemented by a function, by an input preprocessing function, phi, just like in the nonlinear transform. And you do your learning with the z's. Okay, and now when you want to compute your final hypothesis for the raw original input, so you want to compute g of x. You first transform the data to phi of x and implement the learned hypothesis on the transformed data. So this is no different from what we did when we talked about nonlinear feature transforms. Okay, and we're going to now design input preprocessing transforms that will, for example, take your raw xn, which might have arbitrary scalings in each dimension, and produce zn's, which will not. Okay, so let's start with three very basic transforms. They come at almost no cost, very easy to implement, and so you should implement them because it puts the data into this, standard format. Okay. Since the algorithms are expecting this, you'll get a lot of benefit by just systematically always input preprocessing the data into this standardized forms. Okay. The first is centering. Okay. So imagine that your raw data x, I'm just showing two dimensions, but imagine that your raw data, x1 up to two-dimensional x1 and x2, and I'm showing the blue dots. Okay, centering, very simple. Shift the data. Okay. Shift the data so that the center of the data aligns with the origin. Okay, and I'm showing on the right, an example of well, not an example, but for this data, what would the centered data look like? You just you shift every data point. So Zn is just the corresponding xn, so the transformed data point is the corresponding xn minus the average data point. Very easy to implement. Okay. And notice that this is a reversible transform. So given the Zn, you can, as long as you stored, as long as you remembered the mean x bar, you can recover the xn. So there's no information loss. Now, if you look at the original data, the raw data, you'll see that, they're off center. What that means is that the average data point is not at the origin, but for the transformed data, the average data point by construction will be 0, okay, because the average of Zn is the average of xn minus the average of xn, minus the average x, which is the average of xn. So that's 0 minus, that is average minus average, which gives you 0. Okay, and this is a very easy transform, basically no downside. So from now on, we will assume that we've centered the data. What's the next thing you can do? Well, what I'm showing in this blue data here, you can see that the scale of the x1 dimension seems to be smaller than the scale of the x2 dimension. Okay? And that also is preserved in the centered data. So the scale of the z1 dimension is different from the scale of the z2 dimension. Okay? So the next input transform after you have centered is to rescale. Okay? So this is called normalizing the data. So what have we done? We have multiplied the z1 dimension by a constant and multiplied the z2 dimension by a constant, okay, and that effectively rescales each dimension independently, okay, so that now the spread in each dimension is roughly the same. Now there are many ways to normalize. You can normalize in terms of a min-max range. So you might want the min to be -1 and the max to be +1 in every dimension. This is something you explored in one of the assignments. A more typical way of renormalizing is to ensure that the variance in each dimension independently is 1. Okay? And that corresponds to scaling each dimension by the inverse of the standard deviation of that dimension's data. Okay? So this corresponds to taking Zn and multiplying by a matrix D, corresponds to taking Xn, multiplying by a matrix D, okay, to produce the transformed vector Zn. Okay, where this matrix D is a diagonal matrix, okay, and all the entry, the diagonal entry dii is 1 over the standard deviation for the corresponding dimension, so 1 over sigma I. Okay. After you have transformed in this way, after you have normalized, after you have rescaled each dimension, if you compute the variance of the z's in each dimension, you'll find that the variance is 1. So I won't go through that little derivation. It's very easy for you to convince yourself. Okay, Last example of a simple transform, whitening. Okay. Now, look at the difference here. Now, whitening, so again, normalizing, very easy to do, and almost no reason not to do it. So it now puts all the data, all the dimensions on the same scale, and that's perfect for weight decay, perfect for, Euclidean distance, and so on and so forth. And again, this is a reversible transform, so there's no information lost. As long as you remember the matrix D that performed this transform. Now let's talk about whitening. Okay, so what's the difference? So we've now rescaled the data. You'll observe that this data is not sort of spherically symmetric. So basically what whitening does is it makes the data spherically symmetric. Now this transform is not necessarily always done. So raw data centering, almost no reason not to do it. Normalize, almost no reason not to do it. Well, in some situations you may not do it. Okay? If you believe that the dimensions that were chosen were not arbitrary, then you don't want to normalize it. But whoever is in charge of collecting the data has made a design choice that yes, Z2 should be twice. So, okay, so you have to think a little bit about normalizing. Centering, always do it. Okay, and now whitening essentially makes the dimensions independent. So it takes this sort of correlated data and produces uncorrelated data. And so that's what's called a whitening transform. So if you look at the variance covariance matrix of the normalized data, okay, let's call that sigma. So sigma is the sum of the outer products, the average of the outer products. It's equal to 1 over n times the data matrix transpose times the data matrix. Okay, so you can work all these details out. Why is it the sum of the outer products, not the sum of the outer products minus the outer product of the means? Is because we've assumed that you've centered, so the mean is 0. Okay, and so if you take your original data multiplied by the sigma to the minus 1/2, okay, now what is the definition of sigma to the minus 1/2? So sigma to the minus 1/2 times sigma to the minus 1/2 is supposed to be the inverse of sigma. Okay, and we will quickly prove once we get to the board that this whitening transform actually does whiten the data. What does that mean? So once you perform this whitening transform, the covariance matrix for the transformed data will be the identity. So normalizing, what did it accomplish? It set the variance of each dimension independently to 1. But there could be covariance between Z1 and Z2. Once you whiten, you not only have the variance along each individual dimension equal to 1, but the covariance between any pair of dimensions is now 0. So the covariance matrix of the transformed data is basically the identity. And, I'll leave it as an exercise for you to prove that, if you implement this transform on the raw data xn and compute z, the sum of the outer products for z of z and zn transpose, okay, the sum of those outer products, you will find that you get a sigma that cancels out the sigma inverse, and so you will get the identity. Okay. I leave that as an exercise. So, raw data, nothing to lose by centering. Always do it. You have centered data. Now, you typically always want to normalize, unless the person who collected the data said, don't normalize because this dimension is twice as important as that dimension and its scale is twice as large as that scale, and I want it to stay that way. Okay. Otherwise, you'll typically always normalize. And then whitening not only normalizes but also decorrelates. Now, whitening is not necessarily something that everyone always does, but it can be useful if you're not going to do anything more sophisticated afterwards. So then, once you whiten data, these dimensions can be treated independently. If you don't whiten data, and let's say you do a linear model and it has a weight W, 1 on Z1 and 1 on Z2, well, those are correlated dimensions, so you don't really know, how important is the variable Z1. What happens if the weight on Z1 was close to 0 and the weight on Z2 was large? Well, because Z2 and Z1 are correlated, there's the fact that Z2 has a large weight is kind of indicating that Z1 has some role to play because Z1 is related to Z2. And it's typically the case that when variables are correlated, it's easier to overfit. Okay? And when variables are independent, it's typically harder to overfit. Okay? There's going to be less overfitting. So you can read the text for more detail. Okay? So simple transforms that are easy to implement and usually no downside. Okay? Now, hidden danger, especially with things like normalizing, whitening, and so on, centering, and so on. Okay. warning. So you're taking your data, you're choosing a transform. So in all these cases, look, the transform to Zn involves, looking at the data. Your transform, because the mean of the data involves the data. Your transform to Zn involves the standard deviations along the various dimensions. So that means you have to look at the data. And in whitening, you're really looking at the data because you need to compute the covariance matrix for the data points. And then you're going to transform using that covariance matrix. So you have to look at the data. So all the input processing, pre-processing transforms look at the data. Now, if you're going to look at the data, you had better make sure you're only looking at the training data. Otherwise, you're data snooping. So if you've set aside a test set, but you did your let's say normalization before setting aside the test set. So you choose the scales of the data using all the data, then you set aside a test set, you have data snooped. Because properties of the test data have affected the training data, which will then affect the final hypothesis. And if a data set affects the final hypothesis, you cannot use that data set to evaluate the final hypothesis without taking into account that data snooping. So, as a rule, first create your test data the moment you see the data. So the moment you get the data, lock it in a vault, your test data. Now, okay, so that means that you've split your data into the test set, which is in a vault, and your training set, where you can do input pre-processing, as much as you want at will. Okay, do centering, do normalizing, construct your input pre-processing function phi. Okay, construct your pre-processed data z. Okay, do your learning. Okay, get your GTIL. Now open the vault. Okay, get your test data and apply GTIL, which was learned on the Z, to the transformed test data. Okay, and that gives you a test set. And only then is your test set an unbiased and unsnooped estimate of the test performance of GTIL or your final hypothesis G. And on the right, I'm showing you an example where all we did in the text is a little bit of data snooping to decide, the mean vector for centering, in the centering input pre-processing step. Okay. And in finance, if you do any kind of data snooping, it's devastating. Okay. Because the mean of the test set tells you, in some sense, whether the test set is high or low. And so if you use that to predict your trading strategy, you make a lot of money. That's the red curve. Okay. And without snooping, you don't make any money. Now, if you think that you're going to make a lot of money because you snooped, and then you put a lot of money on trading in the test deployment phase, what you'll actually experience is the non-snooped version. So you have just conned yourself. Okay. So, warning. Transforming data into a more convenient format has this hidden trap which leads to data snooping. Very often people, do the normalizing and then say, oh, you know what, I need to have a test set. And many of you have already recognized on one of the assignments that we implemented this kind of data snooping. Many of you found this out. Many of you even corrected it. Okay. This is one of the most subtle forms of data snooping, is when you do input pre-processing before you set aside your test set. Don't do it. Okay. Now, let's go to the board. I'm going to tell you about this powerful technique called PCA. And it's a very powerful technique. It's a very commonly used technique, and there are even nonlinear versions of it, but we're going to discuss the linear version of it. So we're going to discuss linear PCA, principal component analysis.